Okay, so welcome everybody. So today we have Raffaella Schneider from Rome, who will be giving a talk here. And so she's working in the extragalactic group in cosmology and the high redshift universe. And her main research interests are the nature of first stars, preferential sites of formation, and their impact on the overall evolution of the universe through reionization and metal enrichment. She has been recently awarded a ERC starting grant, so she's now building up this group. And she's also how do I say it? Are you the organizer of the Dark Ages Virtual Department? Yeah. David, called David, a nice name. And so today she's going to talk about first stars and galaxies. So, and let's welcome her to Heidelberg. Does this work? Oh, the battery is empty. I'll start to see that.
So thank you very much for this kind invitation. I'm really happy to come and visit Heidelberg. I think it's really one of the most important places in Europe for a person working on first stars and galaxies. And so I hope that I will not be too boring, because some of you are the most important experts in the world, working both on the theoretical side and the observational side. So I'll try to be to give my personal point of view on what we currently know about the first stars and galaxies. And before that, I would like to introduce my team that we are currently building up in Rome, and some of the closest collaborators that are working at this first stage of the project that are based both in Rome, in other Italian institutions, and abroad. And as Hugh was mentioning before, we are part of a larger collaboration focusing on the study of cosmology and the high redshift universe. And as always in these talks dealing with the first stars and galaxies, it's mandatory to start the presentation with the cosmic ladder, where, as you can see, we have at the bottom of the ladder representing the universe, and at the top the most distant view of the universe that we have through the cosmic micro background radiation. And thanks to the enormous advancements that have been made in observational techniques, we are now really starting to peer into this first effort of star formation and galaxy formation in the universe. And but it is likely that in order to have a direct view of the first stellar populations, probably through their associated GRBs or supernovae, we will have to wait for the next generation of telescopes. And since then, the study of this first method of star formation in the universe is essentially based on theoretical models and numerical simulations. So what is the physics of these very early phases of star formation is telling us about the nature of the stars? Well, as you may know, in the last 10 years, a kind of standard model for the formation of first stars has been proposed and indeed confirmed, at least in their basic feature, by detailed numerical simulations. And the physical arguments are quite simple. At the beginning, the gas is cooling and condensing in these very first mini halos at high redshift. Their total mass is about 1 million solar masses. They realize at redshift between 20 and 30, and the only available coolant in these extreme conditions is molecular hydrogen. And in fact, if you plot the evolution of the temperature versus the density of a primordial cloud, and let it collapse, all the features that you see in this evolving equation of state are related to the microphysics of H2. So as you can see, you have the first phase of cooling due to line emission. Then there is this flattening of the equation of state, which is related to the non-LTE, LTE transition in some of the populations of the most important levels. And then you have an increase in temperature, slight increase due to three-body H2 formation, and again you continue to increase the temperature until at the end all H2 is dissociated and the gas becomes optically thick, and you form a central hydrostatic core. The mass of the hydrostatic core is about 0.01 solar masses, which is not different from what we observe in local star-forming clouds, but with a big difference, which is essentially related to the envelope of material that is surrounding the central core. And this envelope of material has a mass which is roughly the Jeans mass at this inflection point of the equation of state. And is, as you can see from the diagonal lines which show constant Jeans mass values in this plane, it's roughly of the order of 10 to the 3 solar masses. So you have a central small hydrostatic core that is accreting matter from a big surrounding envelope of material with a mass of the order of 10 to the 3 solar masses. And the accretion rate onto the central core is very high because of the higher temperature compared to local star-forming regions. The temperature, as you can see, is typically of the order of a few hundred Ks. So you have a high accretion rate, and in the absence of other physical processes, the accretion rate will let the small hydrostatic core grow and accrete all the surrounding matter, available material in a very short time. However, there are some additional physical processes. These are related to the effect of radiative feedback from the growing protostar on the surrounding accretion, on the surrounding gas. And as you would see, this is an important effect which actually, according to the most recent calculations, limit the mass of the star to a range between 40 and 100 solar masses. So smaller than what it could be available to grow from the surrounding envelope material. And as I said before, calculations done with full hydro holes starting from cosmological initial conditions have basically confirmed, or at least robustly described the first phase of collapse. So initially they go from the large-scale structure down to the formation of a newborn protostar. You see in this simulation by Yoshida and collaborators, they could, at the end of the simulation, resolve the 25 solar mass radii around the newborn protostar. It's fine, okay. Thanks a lot.
Yeah.
The second one. Thank you very much. And in a self-consistent way. And what we could see indeed is the formation of a central small hydrocore, and the infold is at the beginning at a very high rate, spherically symmetric, and so they could extrapolate from these to later stages and physically confirm the naive picture that I gave you before. This, at least until 2009, 2010, when recently improved simulations have beginning to paint a different picture. And in fact, here I show simulations that you may all be very familiar with because it has been done here in Heidelberg, where indeed you can see that after the first phase of collapse, the gas starts to get accreted with non-negligible angular momentum, a rotationally supported disk develops, and this disk becomes gravitationally unstable. So you can form, as you can see here, you can form several fragments. And there are still, it is still on debate on whether these can be stabilized by additional heating sources like matter nucleation or small-scale turbulence that is not resolved in this kind of simulation, so it's still debated. But however, even pushing the simulation further, like in this simulation done by Thomas Wright and collaborators, they continue to see fragmentation taking place. Now, what is the fate of these secondary fragments that are forming around the central primary clump is still an open question. In this simulation, for instance, they were able to follow the evolution only for the first 10 years after the first collapse. So it's really too small amount of time before driving some general conclusions. However, what we saw is that about 2/3 of the fragments are rapidly accreted, rapidly migrate to the center and merge with the primary clump. So, for instance, they were discussing whether this can be considered to be a new kind of clumpy accretion mode instead of the smooth accretion mode that we were considering before. But occasionally some of these clumps may be ejected to higher orbits. And so these are the clear examples of a possibility to form low-mass stars very early on from primordial gas. So it can change the paradigm from having a single massive object in each of these mini halos to a clustered mode of formation with some, at least occasionally, small-mass stars. Of course, there are additional important details that cannot be fully considered in such a already extremely complicated numerical simulation, such as the fact of radiative feedback. And so additional attempts were made to model radiative feedback and the accretion phase in a self-consistent way into these simulations. Here, for instance, you see the breakout of the H2 region during accretion. So as the star grows in mass, this H2 region grows, and at the end photoevaporates the disk, so stopping the accretion. And in fact, here is the accretion rate as a function of the stellar mass. In the case of no feedback, you can see that the accretion rate remains significantly large for up to stellar masses of 60 sort of masses and beyond. Whereas if you consider in a self-consistent way the accretion generated by the growing protostar, you are able to switch off the accretion when the star, in this particular simulation, when the star has reached roughly 40 solar masses. So it is still, there are still large uncertainties related to what is the final fate of this process of star formation in the early universe, and we have no essentially clue on what is the exact top-3 initial mass function, which is an additional question. What I think we can say is that the characteristic mass of this star is likely to be larger than what we find in the local universe, simply because the physical conditions are so extreme. We could say that how large is probably a few tens of solar masses. There are probably no supermassive stars as we initially thought after the first numerical simulations. But we have very little clue on what is the mass spectrum, the distribution of stellar masses. And this is quite unlucky because, of course, the end products and the impact that this first stellar generation has on the overall evolution of the universe will depend on the population tree initial expansion. So here I draw a possibility. We have a flat, let's say, flat INF spanning the range of core collapse supernova progenitors with a tail, possibly extending to larger progenitor masses, where we could have some contribution from these extreme parent stability supernovae. And this is well-known phase diagram for population tree stars published by Hagen and Woodley more than 10 years ago now, where you have the final stellar remnant mass as a function of the initial mass for non-rotating zero metallicity star, and in green you have exactly the range of stellar masses where the star could actively produce metals and inject metals in the surrounding gas, so contribute to metal enrichment. However, the analysis of the most recent simulations have shown that clearly that these protostars are born rapidly rotating. And here you have an example of a star, a primary star, which is growing at the center of a of a Mendeleo. 4 different Mendeleos are shown here. So 4 different examples where you have in solid the rotational velocity dash the critical velocity for the star, and you see that in all cases the rotational velocity is between 80 and 100% of the Keplerian velocity, and it persists even after multiple merger events. This solid line here shows the number of merger events that the primary star is experiencing with these secondary fragments, and in spite of that, the rotational velocity is maintained to be significantly large. So
can I interrupt and ask why is it super Kepler?
Yeah, because I had the same doubt, and the authors say that it is due to a kind of averaging effect that they have when they have to compute it in the simulation. So it is probably not feasible. And so it is important to take rotation into account when you consider the final fate and what would you produce at the end of the very short evolution of this massive star. And here, in fact, is a nice result from Björn et al., where they have reanalyzed the Hegel and Woodley phase diagram, taking into account the effect of rotation, and you see you have a whole range of possibility of possible final fate for this star in this mass range. And above this line, the star evolved in a state of complete chemically homogeneous state. So it's a very different evolution where you can even have some possibility to activate gamma ray bursts. So this is quite interesting for observation and search. And in this case, metal production could come from the whole range of possible stellar masses, from 40 to about 250 solar masses. So it's clear that after these first supernovae start to enrich the surrounding gas by the products of their nucleosynthesis, the physics of star formation will change. And we expect that just because of the very simple physical arguments that we were discussing before. So once you have an increased amount of metals, you expect to have an increased cooling rate. And this is, of course, changing the process of collapse of gas clouds. And in fact, over the years, we have examined this problem in detail using essentially a semi-analytical model with a full chemistry. And what we find actually is that we have 3 different mass scales. By mass scale here, I am referring to this characteristic Jeans mass of the unstable gas cloud. So remember, this is the typical thermal track of a metal-free gas that we were discussing before. And I said that this was an important mass scale, the Jeans mass at the inflection point of the original state. And this is clearly, or it's not clearly, but it is suggested by the theory of gravitational fragmentation to be, at least in the present universe, related somehow, this characteristic dynamical scale of star formation to the peak mass of the IMF. Of course, this is a big stretch. There are a lot of physical processes going on, but it is an interesting suggestion. And I wanted to put this figure here just to guide your interpretation of the tracks that I will show you in a minute. So what happens when we increase the metallicity? You start to see a deviation, even a very low metallicity at 10⁻⁷ solar. You start to see a deviation, and first the deviation is occurring at high density, and as I increase the metallicity, you will see that the deviation is more and more pronounced, essentially at low densities for the largest metallicity that is considered here. And as you can see, you start to have additional inflection points of the equation of state, and these inflection points are somehow related to additional phases of cooling and fragmentation of the gas. So compared to the zero metallicity phase, you have some additional fragmentation epochs that are related to different physical processes. and in particular at low densities, the dominant cooling agents are oxygen and carbon chloride cooling, whereas at high density, the dominant cooling agent is collisional excitation of gas grains followed by thermal emission. So here are the metals in the gas phase which are playing the most important role, and here are metals locked up in dust grains which are contributing to the thermal emission. And of course, being important and effective at different metallicities, and because as you have seen, gas cooling start to be effective at lower metallicity, around 10 to the minus 6 solar, light cooling start to be effective at larger metallicities, and but being effective even at different densities, and since the Gibbs mass is depending on density, the typical fragments that you form through light cooling and through dust cooling are very different, and are of the order of tens of solar masses in the first case, and of the order of subsolar masses in the second case. So here we have three different mass scales which are related to the composition of the gas out of which the stars are forming. And to show you that indeed dust is playing a very important role, a major role, I would say, at very low metallicities, I want to show you this numerical experiment that we have done. Here you see the comparison between the metal-free track and the green track is assuming a total metallicity of 10 to the minus 4 solar. And here what we are changing is the so-called dust depletion factor, that is the ratio of the mass of dust relative to the total mass in heavy elements, metals and dust. So if you start with a 90% depletion, meaning that most of the elements are in dust grains, you have a very strong deviation from the metal-free case. As you reduce the depletion factor, so you transfer elements from the dust grains to the gas phase, you are getting closer and closer to the metal-free case. And why is this occurring? It's clear at high density you have a smaller amount of dust available to cool the gas. But here it's also a significant increase in the cooling rate, and this is despite the fact that you are returning part of the metals in the gas phase, and this is due to the fact that still at 10 to the minus 4 solar, the dominant cooling here is provided by molecules, OH, CO, water, and NH2, of course, and these molecules form on dust grains. So if you reduce the abundance of dust grains, you reduce the molecules and you also reduce the cooling rate. So that's to show that even at these relatively large for in primordial terms, metallicity, which is 10 to the minus 4 solar, dust grains are important for the thermal evolution of the clouds. So clearly dust cooling depends, as you see, on the absolute metallicity and on the dust depletion factor, so ultimately on the dust-to-dust ratio. And in fact, we, having explored a large parameter space where we essentially consider the contribution to enrichment of these clouds by different supernovae, and even assuming the local ISM composition rescaled, simply rescaled to lower metallicities just as experiments, we could essentially populate this diagram where on the y-axis you have the depletion factor and on the x-axis you have the total metallicity, and we could divide this parameter into this plane in two different sub-regions, where a region where you don't have fragmentation, so you are not able to activate this fragmentation mode, and a region where you do have fragmentation. So in principle, in this region you could form normal stars. And this dividing line is a critical dust-to-dust ratio of the order of 4 times 10 to the minus 9, and this number can be easily derived by assuming that the energy transfer rate between the gas and dust is larger than the compressional heating rate at the time when dust cooling becomes important. And in fact, this inequality leads exactly to this number once you take into account the effect of the total grain cross-section, which we typically have. So this is a different view, pictorial view of this so-called critical metallicity scenario, where again you see that you have a top 3 star-formation mode, meaning a mode of star-formation which preferentially form big stars, large fragments at least, and a low mass formation mode where you preferentially form low mass stars, and in this critical range of metallicities, the fate of the clouds will depend on the amount of dust that are dispersed. So the question now is, how can we possibly test this scenario? Well, we need to have some predictions on what are the products of these first stellar explosions. We need to then be able to follow the products of these explosions and the mixing of the produced heavy elements with dust into the next generation star-forming regions. And then we have to make observational predictions to be comparable with what we observe today in the present universe, in the most matter for stars that you are collecting in the galactic halo and in nearby worlds. And since 400 days after the explosions, we have started to collect evidence for dust formation in supernovae. This is the case of 1997A, and this is the most studied supernovae, and so it's almost real-time astronomy because they can follow the build-up of the dust mass through the evolution of the ejecta. So you know very well there is this structure, the ejecta and the ring structure, and here is a very nice plot shown by Mikako Matsura in her paper a couple of years ago, where she was connecting the flux observed with Spitzer and the flux observed with Herschel at long wavelengths, and these are clearly 2 different peaks in the emission. One is associated with dust that has been probably ejected by the progenitor and is associated with the ring structure, so it is essentially emitting at a higher temperature, at lower frequency, at lower lambda, and instead at after Herschel was able to have observations of these supernovae, we could finally see the real ejecta dust, the dust which is produced by the condensation of heavy elements in the ejecta, and the amount of dust ranges between, as you can see, 0.4 to 0.7 solar masses, so it is orders of magnitude larger than what could be inferred by observation of longer medium. So what are the models for dust formation in supernovae telling us? Well, there have been several attempts by different groups to model dust nucleation in supernova ejecta, and most of these models are based on a very simple approach. So standard nucleation theory, at a certain point, the conditions in the ejecta are favorable to dust condensation, so the temperature and density is favorable to dust condensation, so you form the first seed clusters and then you accrete the possibly heavy elements onto the seed clusters, and you build up the dust mass. And with Simone and Bianchi, some years ago, we have tried to explore what are the uncertainties related to some important parameters of the theory. For instance, the so-called sticking coefficient, which measure the probability of this ring growth, and the number of minimum monomers that can compose a seed cluster. So these are all things that are familiar to people doing standard nucleation theory, but are very relevant, as you can see from the variations for some of these. This is the mass of dust as a function of the stellar mass. So for some progenitors, you have order of magnitude difference in the amount of dust that can be produced. So clearly, these macroscopic parameters are very important. And not only that, this is the prediction for solar metallicity supernovae. If you change the metallicity of the progenitor, or if you change the rotation rate of the progenitor, you also expect to have differences. And most importantly, when you make comparison between theoretical predictions and observational data, depending on the age of the supernova, you also have to take into account that the newly formed dust can be partially destroyed by the reverse shock, by thermal scattering in the reverse shock. So before the dust can find its way to the alien sun and really contribute to metal and dust enrichment, it has to suffer this partial destruction. And in fact, here we have explored different cases. So this is just after the condensation, and you can see that only between 2 and 20% of the newly formed dust is able to survive the passage of the reverse shock. And this somehow depends on the density of the circumstellar material where the explosion is taking place. It's a measure of the shock velocity, of the reverse shock velocity in rough terms. So, yes?
Are there not empirical constraints on how much dust survives from supernova remnants in the galaxy?
Yes. In fact, well, empirical, I will show you a rough comparison with what we have in terms of observations. So, this I already said, there are dependence not only on these macroscopic parameters, but also on the physics of the supernova themselves. So the metallicity, the energy, the mass cut, the rotation, all these factors will affect the final amount of dust. And here in Rome, we are currently trying to explore all these different effects to at least understand what is the most important one in terms of dust collection. And in fact, here just to answer, this is a collection, probably not updated collection of dust mass inferred for young supernovae and supernova remnants. This is the age of the supernova and the mass of dust estimated from observations. And this is given to me by Raffaella. And you can see that most of previous calculations, most of previous observations were significantly underestimating the total amount of dust that is produced in this core collapse event, because probably they were missing the cold dust simply because of the wavelength coverage of the observations. And in fact, here is the point of Herschel, and you can see how it has increased significantly, as I was showing before in the analysis of this astronomical distribution. And instead, as for the supernova remnants, we know that supernova remnants, actually it was quite a puzzle at the beginning because we could not easily explain why we had such a small amount of dust observed in young supernovae and then such a big amount of dust observed in supernova remnants, unless these supernova remnants are heavily contaminated by interstellar dust. So it's not what you're seeing, it's not associated to what was produced by the progenitor. But now, I think with the Herschel detector detection, we can have space to partially destroy the newly formed dust and this be consistent with supernova remnants observations.
So you're implying that all the other data points in the bottom left of the plot actually have a factor of 1,000 higher dust mass. You have all these in the bottom left, right?
Okay, so
all of these are underestimates by a factor of 1,000 in dust
yeah,
mass.
they're probably looking at different dust components. As I showed you for 1987A, I think now it's pretty clear, and I'm looking forward to have the new ALMA observations because ALMA will have also the spatial resolution to discriminate these two different components probably. But what it is thought, and also what it is modeled by radiative transfer models, is that this warm dust is associated with the ring, and it contains only the small amount of dust that has been produced by the progenitor through a wind phase, and instead the bulk of the mass that is produced during the explosions in the ejecta is emitting at much longer wavelengths. So it's already cooled down and was completely missed by previous analysis. So suppose we now have at least a way to control what these first supernovae can produce in terms of metals and dust grains. We now have to predict how they contaminate the nearby star-forming regions where second-generation stars form. And here I will show you a an old simulations that we have done together with Luca Tornatore, where we were just trying to understand this point. So we were following the mass average metallicity and the fraction of metals coming from population T stars. And you will see in the movie in a minute that blue corresponds to very metal poor regions, yellow corresponds to already metal rich regions, and here red essentially means that 100% of the metals are produced by population T stars. So it's really a way to mark the location of these top 3 star-forming regions. Of course, this it's a topic that has been analyzed by many different authors with more sophisticated numerical simulation, but this is just to give you an idea. If I can't wrongly. Okay. So at the beginning, you have a few isolated star-forming regions, as you can see, but they quickly enrich their surroundings, and the enrichment is from the inside out. So you have at the end these very large metal-enriched bubbles, which are quite metal-rich in the interior, but you still have some relatively metal-poor gas in the outskirts or in few isolated regions. And this is exactly where people like Max Bettini, who came here a couple of weeks ago to give one of these colloquium, are looking for to have some hints of top 3 signatures in these isolated but relatively nearby regions or really at the outskirts of larger collapse structures. And as you can see here from this other movie, the fraction of top 3 metals in red, you see the location of these top 3 star-forming sites, again, are either in isolation or at the outskirts of these larger regions. And you can still have some regions where you can, in principle, continue to form these top 3 stars even at relatively low redshift. Of course, they will be subdominant. But what I think is more interesting for what I have to tell you is what is the typical metallicity distribution of star-forming region in these first protogalaxies. And using the data of the simulation that I showed you before, we could compute what is the typical metallicity of star-forming regions at different redshift and 8, 6, and 4 as a function of the halo mass where these star-forming regions are hosted. And this is the stellar metallicity at the same 10, 8, 6, and 4 redshifts. And what you can immediately see is that you have a very large spread in metallicity at the lowest protogalactic masses, I would say, and then a flattening towards a plateau in larger systems. And also that there is a very little or no redshift evolution. And this indeed has been confirmed even by more recent numerical simulation. This is, for instance, a very nice work done by John Wise and collaborators using higher resolution simulations coupled with radiative transfer, so it takes into account both chemical enrichment and radiative feedback, so it's a very complete work. However, as you can see here, this is the metallicity of produced of regions contaminated only by top 3 stars as a function again of the post-halo mass. And you can see again that you have at lower masses a large spread in metallicity values, and at larger masses, you have a plateau of the order of 10 to the minus 3 solar masses. And this is again almost redshift independent. All these points refer to different redshifts, and you can see it's quite redshift independent. So it's nice that even if the 2 simulations were done with very different techniques and different resolution, this result appeared to be quite robust. So what is the fate of stars that would form either here or here? Well, clearly, as I said before, the fate would be very different. In particular, stars that will form in larger systems, so second generation stars that will form in larger systems will be sitting here. So they will clearly produce low mass stars and long-lived stars without any problems. But stars which will be in lower mass systems or lower mass halos with this large spread of metallicity value, well, their fate will depend on how much of the dust that is produced by this first supernova will be able to survive. And just to refresh your mind, this is exactly what I was telling you before. So unless you will be, so if you have a sufficient amount of dust in these early phases of enrichment, the stars that will form here will be able to survive and be observable at redshift 0. So this brings me to the last point. I don't know how much time do I have left?
We still have around 10 minutes.
Okay. To the last point, which is how can we try and hope to put constraints, observational constraints on this scenario. And I would, of course, I would like to start by quoting Norbert Frieslieb, who in Raleigh a couple of weeks ago showed this sentence in his presentation. So sometimes the fact that we do not see some things is more telling than things we do see. And this is very, I think, very appropriate in this case because no metal-free star has ever been observed. Okay? We can argue if a truly metal-free star would be ever observed for many reasons. There is a pollution limit, there are difficulties, but I think it's still, we can take this result as at least an empirical indication that population-free stars were more massive than one solar mass. But of course, there are many things that we do see, and here is a table that I took again from his presentation, where you see a number of surveys that are ongoing, and the number of stars that have been measured with an F over H less than -3 or even less than -5. So we are really pushing the limits of our observational capabilities to put constraints on these earliest phases of chemical enrichment and star formation. So the first thing that is very interesting to take into account is the metallicity distribution function of the galactic halo. And here we see the shape of the MDF, and at the lowest metallicity tail, these four stars that are populating the MDF at F over H less than -4.5. And the question that we had asked some years ago was, what is this low metallicity tail of the MDF telling us about the POP3, POP2 transition? So when really low mass stars can start to form and survive until the present day. And this is an example of what are the possibilities of theoretical models. So for instance, in this case, we have done 100 different merger tree histories of the Milky Way halo, and then we have coupled these merger tree, dark matter merger tree histories with a semi-analytical code where we could follow the transition, the POP3, POP2 transition and the enrichment. And this is the average of the many predictions of the many realization with the 1 sigma scatter compared to the observational data. And in this case, we were very simply assuming two different values of the critical metallicity above which low mass star formation could form. And as you can see, as it would be expected, if you decrease the critical metallicity, you start to populate the low metallicity tail of the MDF. If you cut the transition at the higher level of metallicity, essentially you miss all these stars here. Now, there is a problem, however, with this argument that we know that at least 3 out of these 4 stars do not have a very low metallicity. They just have a very low Fe over H. And in fact, here are the 4 examples with, as you can see, an Fe over H ranging between -5.4 to -4.75. So really very, very extremely metal-poor stars. However, if you take into account the additional elements that have been observed on the surface of these stars, 3 out of these 4 stars have a total metallicity which is several orders of magnitudes larger than what you could infer from the Fe over H. The only one is the Raffaella star, a star that Elisabetta has observed a couple of years ago. And when I first read this observation of result, I have to say I literally jumped on my chair. I said, this is it. This is really what I needed. And in fact, this is a clear example of a star that has a very low metallicity, yet it has a low mass, so it was able to form somehow. And according to the three mass scales that I was showing you before, this star, the abundance of oxygen and carbon that is required in order to fragment and to produce a low mass star is okay for these three stars, but it is not enough for these stars. So the minute later I rushed into my colleague's room in Rome, Marco Limonge and Alessandro Chietti, and I said, we need to have an interpretation for this star. We need to try to really simulate what was the environment where this star could have formed. And the first thing that we did was actually to try to reproduce the best that we could the observation the surface elemental abundances of the star with some models. So they have this code. They could explore different progenitor models, and we of course assuming zero metallicity. And we pick up two possibilities which appear to have the best, the closest agreement with the observation data. And these two were two different progenitor masses of 20 and 35 solar masses. And then, with these supernova models in my hand, I rushed back into my office and I started to compute what was the associated dust yield, using our model, having the full information about the supernova evolution and the explosion energy and mass cut and everything. We could simulate what was the amount of dust that was able to be produced by these two different supernova progenitors. So this you see the dust mass as a function of the different dust pieces. So you have carbon grains, silicates, magnetite, alumina. You have many different dust pieces that can be formed. And on top, the top histogram shows you the abundance just after, right after the condensation phase, so a few hundred days after the explosions. But then we also took into account, having no clue on what was the density of the circumstellar material when the explosions took place, we had to take into account different possible destruction efficiency by the reverse shock. So we were exploring possible different destruction efficiency which affect, as you can see, not only the total mass of dust, but also the dust composition in different ways, because each species has its own grain size distribution, and the smallest grains are affected more than the larger ones. So at the end, we had a parameter space to explore, and then what we thought is, okay, let's suppose that now one of these two supernova progenitors have enriched a nearby star-forming cloud exactly to the total metallicity that is observed for this, or it is estimated for this Cat star, and see what happens if there is enough cooling available to form low mass stars. And this is what we did. So we fixed the total metallicity to the observed total metallicity of the star. So this somehow fixed the dilution of the heavy elements and grains produced into this new star-forming environment. And then for the two different pollution channels, let's say, we followed the evolution of this star-forming cloud. And as you can see, in all cases you have a first phase of fragmentation, which is taking place at these intermediate densities, and the typical Jeans masses of the order of tens of solar masses, and the dominant cooling here is due to OH. It's not carbon-1, it's not oxygen-2. You don't have enough of these elements available to activate cooling. But then you can have an additional phase of fragmentation. Here the triangles show you the cases where we could have fragmentation compared to others where we do not have fragmentation. So depending on the progenitor mass and on the destruction efficiency by the reverse shock, we could see that at least in 4 out of 8 cases, we could really induce fragmentation. So the dust that is produced and that survives is enough to explain the low mass star observed for this Cat star. The low mass. So I get here to my summary. It's clear that the final outcome of metallicity star is likely to be determined by these two important key physical processes, disk fragmentation and radiative feedback in the equation. So we hope that as new numerical codes will progress and new machines will be available, we will have some final word on what is at least the typical outcome of this primordial star-forming network. What we can infer from what we know is that the spot element is likely to be top-heavy and probably have a tail that extends to other masses, but it will be shallower than the salpeter tail. The characteristic masses are of the order of tens of solar masses. And these stars are also rapidly rotating, so both their masses and their rotation velocities will be important in order to determine the final fate and even the kind of metal industrials that these stars will produce. It's clear that, at least from our analysis, you can have a sufficient amount of dust grains that are able to survive early on, so you can have rapid dust enrichment early on to allow the formation of low mass stars, and we have at least one example of one of these stars. We hope to soon to have more examples of these stars, but clearly stellar archaeology is currently, I think, the best way to really put constraints on these physical processes, and hopefully in the future with new telescopes and facilities we will probably be able to have direct access to these epoch of star formation. But before that, I think that this is the strategy to go. So I really encourage the people here in Heidelberg to do their best to collect more data and help us to put constraints on these formation methods.
Thank you very much. So, other questions?
Can you explain the difference in the physically of this three star where we have a large oxygen and carbon compared to this Kappa star? With the Kappa star, you kind of the second generation star. Only one supernova than 25 solar mass star. And how do you get the other three stars which have lower iron abundance but a high oxygen and carbon abundance?
Okay, this is a very interesting question, of course. And what is, well, from my point of view, the existence of those stars is quite trivial because given that they have this large abundance of carbon and oxygen, and these elements were present in the first place, that they are the most important cooling agents. So it's clear that if you have those two elements from the very beginning, you will have fine structure and cooling and you will form low mass stars. The problem is how can you explain this very peculiar abundance pattern? And to explain this very peculiar abundance pattern, the fact that you have very little iron and large abundance of carbon and oxygen, there have been many different models that have been proposed in the literature. And currently, I think that probably the most solid one, let's say, is that these environments were produced by supernovae, but with very little mixing and strong fallback, meaning that the most internal part of the ejecta will fall back onto the remnant, so you will have ejection only of the outer shells, rich in carbon and oxygen, and very, very little iron. So that it's a way to explain these relative abundances. But as for the cooling properties of the second generation that will form, oxygen and carbon are enough to activate non-cooling science fiction. But I'm sure that even those supernovae will form dust. So you can have both channels. Dust is not strictly required, but you can have it.
You were saying that new machines might allow us to see POP3 at high enrichment. So, if I remember correctly, even in days when POP3 were 100 solar masses, for example, JWST have a very hard time of seeing anything.
Yeah.
What actually specifically,
No, I think
which
more
machine
of,
will do it for you?
no, I'm more thinking of the, I was saying actually machines referring to numerical machines, to machines that can allow us to push these simulations even further to really put constraints on the masses of the stars. But however, I think that the best strategy so far, given that these stars are not that massive, is trying to go after their gamma reversed or their supernovae, and there are even with recent literature attempts to make predictions of the rate of gamma reversed associated to these proxy stars, especially if they are very rapidly rotating, as it might be. You have spaces, significant parameter space, where they could power gamma reversed. This is of course something different than looking at their light. I agree with you. But different possibilities would be, since, as I said, chemical enrichment is not homogeneous, it's highly inhomogeneous. You expect probably to have the first protogalaxies, which would be accessible to James Webb, for instance, to have mixed stellar populations of pop 3 and more like pop 2, pop 1 stars. And then you could, there are attempts where they have shown that the colors of these protogalaxies could be different because of the relative contribution of these two different populations. So another strategy would be to design specific strategies to go after these peculiar colors, and then hopefully be able to quantify the contribution of population of these stars.
So I found it a little notable or strange that there are so few these metallicity from the -4 to the -5, so -4, -5 stars. So the mechanism you explained for the proposed star seems to be very rare. Can you comment on that?
Okay, so we have been discussing this even this morning with Norbert and Rebecca. I should have this nice collection of observational data. This is a collection of observations where Anna Faber and collaborators were using this transition discriminant, which is weighted, as you can see, on the carbon and oxygen abundance, to show, if you plot this transition discriminant as a function of the F/H, to show that most of the stars that have been collected are lying above this transition, this critical line, which is called the forbidden zone for carbon 2 and oxygen 1 So you can see essentially only the Kapau star is sitting here in the forbidden zone. There are additional candidates which are at the border, but only this star is sitting here. So it's clear that this poses a question. I agree with you. And also the fraction, the relative fraction of these carbon-enhanced stars relative to normal star is increasing as you decrease in metallicity. So if you go to very low F/H, you have a larger abundance of carbon-enhanced stars relative to normal stars, whereas if you go at higher F/H, the relative proportion is smaller. So clearly, these are all things that need to be investigated. My point is that, at least for one star, you have a clear empirical evidence that you need something else to form Loma stars beyond carbon 2 and oxygen 193. Okay? Not saying that this would work everywhere, and also that it is relatively easy to produce the little amount of dust that you require for this mechanism to be effective. These are my 2 points. Then, whether this will be the predominant mode in your universe or not, has to be confronted with observations, and clearly larger statistical samples here would be really important to be able to make a definite assumption on that, or statement on that.
Yeah. Right. Coming back to the origin of the dust, if you look at the supernova in our galaxy, even in ones like Cassia, which is relatively high numbers, about 0.1 solar mass of dust, if you compare that to the total sun's mass of the potential star, then it's pretty apparent that those objects are actually destroyers of dust rather than injectors of dust. Certainly, the vast majority of the metals will be injected into the ISM in the form of the gas phase rather than the solid state phase. Whereas in the ISM in general, most of the refractory elements are in the solid state. And if you look at the cycle of dust destruction and injection in the ISM, you rely on an in situ ISM dust formation mechanism for the Milky Way. So my question to you really is, why do you place so much theoretical evidence, after all we've got very little empirical evidence, on dust production and supernova elements, whereas you've got the ISM? For example, when you start forming these cores, can you not produce grains by in situ from the ISM?
Absolutely. In fact, well, to answer the first question, the reason is that supernovae are the first metal producers, okay? And so you may need some time to grow dust in the ISM, okay? So as a first step, you have these metals produced by the supernovae, and then you ask yourself, how much of these metals can be condensed and survive in the form of solid dust grains? So we have, I think, given at least a reasonable evidence that it is not too difficult, even from the primordial supernovae, to produce a minimum amount of dust, which is enough. You don't need more. But then, to answer your second question, once you have polluted the clouds, even with tiny amount of dust, during the phase of collapse, the dust will grow exactly by the same mechanism that dust grow in the ejecta, so by accretion. And in fact, what we have recently investigated with the Japanese group, with Mizawa and a student, again Chaki, was exactly to start from the same initial condition that we have examined in the case of the cacao star, but with the smallest amount of dust. And let's see if even in the few cases where we couldn't see fragmentation, so for instance here, you see, there are some cases where you don't see fragmentation because simply you have destroyed the dust that you had formed in the very first place by the reverse shock. And instead, if you take into account the fact that grain grows during the phase of collapse, you can essentially bring all these lines to the red case. So essentially, this means that you don't really need to rely on the dust that was in the ISM before the initial collapse.
Is the grain growth empirically connected to grain growth in the Milky Way?
Yeah, actually, it is usually calibrated to reproduce the properties of the grain.
Regarding more direct observation conditions at high redshift, what about looking at the extinction curves of bright high redshift objects? We already have some information now from redshift 6 quasars, also gamma burst activators at redshift 6, 7. Shouldn't we be able to do better in that regard by the time?
Well, that's, the extinction depends on the grain properties, on the grain size distribution, and on the optical properties. So you have even there a lot of uncertainties, especially for this primordial dust. However, we did one attempt with Roberto Mogolini some years ago. There's a paper published on that for a quasar, where we suggested that the extinction curve inferred for the quasar was in much better agreement with the prediction of supernova type dust rather than the normal SNC extinction curve that is usually assumed to running these quasars. So this first evidence is already there, and then Simona Gallerani have recently analyzed a larger sample of quasar redshift between 4 and 6, and she saw some deviation from the SNC curve as you go to higher redshift. So this might be an indication that at least the properties of dust are changing as you go to higher and higher redshift. And in addition, in this high redshift quasar, even at redshift 6.4, you have this huge amount of dust. And this huge amount of dust needs to be produced in less than 1 billion years. So really, you require very efficient dust production, at least in these extreme objects, which are chemically evolved objects.
So, final question.
From my understanding, the formation of Kafka stars, you will point into the fragmentation. It could, is the picture that the Kafka star was formed as a single object, or like in the drive simulation that you saw, still in a certain stellar accretion disk of a bigger object, or carbon C?
Well, you could in principle think that the star was formed as one of these secondary fragments, and then that the star has acquired their certain surface metallicity simply by accretion into the repeated passage through the galactic disk, for instance. Or there are models that think that you can form these primordial stars early on at zero metallicity, and then they acquire the metallicity on their surface by simply accretion. You could in principle think to distinguish these two channels by looking at the relative abundances, because in that case I suppose that the abundance ratios would be exactly the same as the ones you have in the ISM. Whereas in the case of the Cacao star, you have typically abundance ratios of the star similar, this star to the average star of the Heidelberg sample.
It was formed as a single object, basically.
Yeah, most likely.
Okay, so let's thank Raffaella again.